webinar is an example. The example is for e-commerce site and the processing of orders. In this particular case, this is the handling of a credit card, processing of the credit card by the back-end payment processing system. So we have 4 conditions: real account, active account, within limits, location OK. Those are shown on the upper left side of the decision table. And we have 3 actions: approve, call cardholder, and call vendor. Those are shown on the lower left side of the table. Now in this case, all of the conditions and all of the actions are Boolean. In other words, they're either true or they're false, or yes or no, shown here. And what we have in the top half of the decision table are the combinations of conditions, and in the bottom half we have the implementation of the business logic that says, okay, under this particular combination of conditions, do this and don't do that, hence the yeses and nos there. Now, this is a interesting type of decision table, interesting form of decision table, called a full decision table. And the reason it's called a full decision table is because every possible combination of conditions is shown there. Now, how do you know that that is true? Well, there's two ways. There are 4 conditions. So how many possible combinations of yes, no are there? If there are 4 variables that can be yes or no, well, it's 2 times 2 times 2 times 2, 2 to the 4th power, which is 16. And you'll notice that there are 16 columns here. So that's one thing that would have to be true. To be a full decision table, it would have to have exactly the right number of columns based on the conditions. Now in this case, they're Boolean conditions, so it's 2 to the n power, where n is the number of conditions. The other thing that you need to see is the pattern that is shown here. There's a pattern that allows you to visually inspect the top half of the table and know that indeed all of the combinations are there. So you'll notice that the first half of the real account row is all yes, and then the last half is all no. And then we split that in half with the active account row, and that's 4 yeses, 4 nos, 4 yeses, 4 nos. And then we split it in half again with the within limits, 2 yes, 2 no, and split that in half again. And now we're down to the lowest level of splitting that could occur, where the alternation is every column is the opposite value. Yes, no, yes, no, yes, no. Now that pattern has to exist for it to be a full decision table as well. So that makes it real easy to construct a decision table, because if you know the conditions that apply, you put them in order, and it can be any order you want in terms of which one comes first on the list of conditions, like real account in this case, and which one comes last, like location OK. And then you build this pattern of yeses and nos, where at the top row you have the first half of the columns are yes, and the second half of the columns are no, and then you split that in half. In other words, the rate of change is twice as fast for the column or the row below that, and then the same for the row below that, and so on, and such that the last row has alternation on every other column. So it's got this nice visually inspectable pattern that you can look at, satisfy yourself, indeed all of the combinations are here. Now, you'll notice, of course, in the bottom half of the actions section, there is no such pattern, and then that's because this is arbitrary. Now, I use the word arbitrary guardedly here, because not arbitrary in the sense that it has no meaning. It's arbitrary in the sense that unlike the top half of the table with the condition combinations, there is no mathematical pattern to this. This is not determined by mathematics or Boolean logic. This is determined by the business logic. And business logic is subject to, in most cases, the whims, decisions, preferences of human beings, and thus not subject to mathematical regularity. Now, there might be special cases where you're dealing with some kind of physics problem or chemistry problem or something like that. You see patterns emerge in the actions. That's certainly possible, but that is a manifestation of the property of the problem that you're trying to solve, not an inherent property of the decision table. So, just to try to summarize that, in a full decision table, there will be a pattern of values in the top half where the condition combinations are shown. There will not necessarily be a pattern in the bottom half where the actions and their combinations are shown. Now, one other thing to mention before I move on. In this case, the conditions are Boolean, and therefore each has two values, so the number of columns is 2 to the n power, where n is equal to the number of conditions. Not all conditions are Boolean. Conditions can be defined on ranges of values. Conditions can be defined on values that have, on variables that could take on 3 values or 4 values or something, and then in that case, that obviously would change the number of columns and it would change the pattern. But it would be an extension of the same kind of thing. So if there were 3 possible values for active account, for example, yes, no, and maybe, assuming that was somewhat indeterminate, then the number of columns would be 2 to the 3rd power, or 8 times 3, 3 for the active account, which would be 24. And similarly, you would expect that the pattern would look different, and that we would have to have 4 yeses, 4 nos, and 4 maybes, and then 4 yeses, 4 nos, and 4 maybes for active accounts. So that's fine. That can happen. You just have to be aware of how it affects this. Okay, now each column in the decision table says, under this particular combination of conditions, take these actions and don't take those actions. So for example, take a look at 7, column 7. If it's a real account, but not an active account, it's not within limit, and the location is not okay, then do not approve the transaction. Call the card holder and call the vendor. Rule number 1, so-called happy path. It's a real credit card account. It is active. It is within its credit limit, and the location of the charge is fine. Approve the charge. Do not call the card holder. Do not call the vendor. Okay, so we've got that decision table. Either we constructed it ourselves, or the nice business analysts or requirements engineers who created the design and requirement specification gave it to us. So either it was given to us or we made it ourselves, but now we have it and we can create tests from it. And basically what you do is you just read column by column and say, okay, I'm going to create input values and preconditions that create the conditions. And then I'm going to verify the actions. I'm going to methodically step through column by column doing that, either creating concrete test cases from each column, or perhaps I'll just decide to use the decision table as a form of logical test case if I can create the values that way and just read the values right onto the test. So that's certainly possible. If you're able to do that, just on the fly, read the values of the column and then create the test from it, then you can do that as well. But the important thing is that you have to have at least 1 test per column. Now, you might generate more than 1 test per column, and I'll get into that a little bit later. Now, if we look at this thing, this table, we have some nonsensical columns. Account not real, but account active. Let's go back here and take a look at that. How exactly would that exist? And the account is not real. The account is active. And we have a number of these kinds of combinations here, which are sort of nonsensical. And how could it be not real, active, and within limit? Or for that matter, out of limit? I mean, what would it mean? The account doesn't exist, so does it have a limit?